Welcome to The Explainer. Today, we're diving into something that honestly feels a bit like science fiction, but it's happening right now. We're talking about using artificial intelligence to predict the absolute chaos of our atmosphere. It's a wildly fascinating journey, so let's just jump right in. So, the core question we're tackling today is this: can an out-of-the-box AI actually predict tropical weather? I mean, think about Indonesia's atmosphere for a second. It's this wild, incredibly complex, and highly volatile system. It is literally the ultimate stress test for any predictive model. Can an AI just step in, look at the raw data, and immediately know when the temperature or humidity is going to spike? Let's find out. Okay, let's map out our journey. We're going to cover the AI weather challenge, how we tune these models with Optuna, the massive drop in uncertainty, real-world monitoring with the BMKG, and finally, the future of forecasting. All right, starting with part 1, the AI weather challenge. To tackle this weather prediction problem, researchers are turning to what's known as a foundation model. Specifically, we're looking at a model called Lag-Llama. Now, think of Lag-Llama as a massive, super powerful engine that's purpose-built to understand time series data. Data that constantly shifts over time, like the stock market, or in our case, the weather. But here's the catch, and it's a big one. While it's incredibly powerful right out of the box, it's basically a generalist. It hasn't been calibrated yet for the extreme local variations of a specific tropical climate. Now, what's really interesting about this visual is those huge, wide red bands surrounding that blue temperature line. This is the model running zero shot, meaning it's trying to predict the weather without any localized tuning whatsoever. That massive red shaded area, that represents epistemic uncertainty. The model is essentially throwing its hands up. It's like taking a high-performance race car and putting it on a muddy dirt road. Sure, it has the raw power, but it completely lacks the calibration to actually maintain its grip. Which brings us to part 2, tuning with Optuna. So to get our race car back on the track, we need a master mechanic. And in the world of machine learning, that mechanic is hyperparameter optimization. The specific tool being used here is called Optuna. As the research highlights, choosing the right values isn't just some nice-to-have bonus. It is absolutely crucial. It's the step that dictates whether the model can actually capture those complex real-world weather patterns. So how does Optuna actually work its magic? Well, it uses this incredibly smart method called Bayesian optimization. Instead of just randomly guessing how to tune the engine, it actively learns. Step 1, it tests a specific setup, tweaking dials and levers like the learning rate or the context length. Step 2, it evaluates how badly the AI messed up the forecast. And step 3, it takes that past failure and automatically adjusts the dials in a much smarter direction for the next try. It beautifully balances exploration with exploitation to find the absolute perfect tune. And it does it efficiently. And the contrast here is just staggering. We go from that zero-shot baseline, the untuned, hesitant AI that's literally casting this huge net of guesses because it doesn't get the local climate at all, to the optimized model. This new version is sharply tuned, it's confident, and it genuinely understands the nuances of the local data. Let's look closer at those results in part 3, sharper accuracy, less uncertainty. And this brilliantly illustrates the change. Remember those massive, messy red bands from the zero-shot model? Just look at them now. The prediction bands have tightened up so beautifully, and they're tracking the actual blue temperature line with incredible precision. The model isn't just making a slightly better guess anymore. It has achieved what we call trustworthy uncertainty quantification. Basically, it knows exactly how confident it should be. Let's put some hard numbers to that visual, shall we? The mean squared error, or MSE, is a key metric telling us how far off the model's exact predictions are from reality. For temperature predictions at the Kemayoran station, the error plummeted by a massive 77% after Optuna tuned the model. At the Kualanamu station, it dropped by 74%. This right here proves just how much more accurate the predictive point has become. Our mechanic definitely fixed the engine. But look, weather forecasting isn't just about picking one exact point. It's about the whole range of probability. Which brings us to this single, absolutely crucial number, 54%. That is the reduction in the continuous ranked probability score, or CRPS, for temperature at Kemayoran. The CRPS measures the accuracy of the entire spread of the model's guesses. So a 54% drop, that proves the model's probabilistic guesses are no longer wildly uncertain. In the real world, this is the difference between knowing it might rain and knowing exactly when to issue a flood warning. It's calibrated, it's sharp, and it's reliable. Now, you might be wondering, out of all the countless dials Optuna was twisting, which one actually mattered the most? Well, the research found that the learning rate was the absolute most dominant lever. Because Lag-Llama is this complex, transformer-based model, it's highly sensitive to how quickly or slowly it updates its internal knowledge, what we call its gradient dynamics. Tuning that learning rate properly was the #1 factor in stabilizing the model and hitting that high level of accuracy. All right, let's see this in action. Part 4, Real-World BMKG Monitoring. The researchers didn't just test all this in a theoretical vacuum. They used historical data from two very distinct stations operated by Indonesia's BMKG. We've got Kemayoran and Jakarta sitting right in a monsoonal climate zone, and then we have Kualanamu in North Sumatra, which is located in an equatorial climate zone. These are entirely different tropical environments, right? So it's the perfect stress test to see if the AI can truly adapt to different local extremes. So, the crucial point is that the AI isn't just a one-trick pony. Check out the optimal configurations Optuna discovered. For Kemayoran's monsoonal climate, the best setup used 6 architectural layers. But over in Kualanamu's equatorial zone, it only needed 5. The automated mechanic went in and found a totally unique engine tune, tailored specifically for each distinct environment. Looking at the percentage improvements across the different weather parameters, it's really telling. Notice how temperature and humidity saw these transformative gains, jumping anywhere from 50 to 77% in accuracy. But air pressure, down at the end there, only saw minor tweaks of around 6 to 11%. Atmospheric pressure is just a much more stable variable, and both the AI and Optuna knew exactly what needed aggressive tuning and what to just leave alone. Which brings us to our final section, Part 5, the future of forecasting. Let's move on and see how this builds out in the future. Currently, this was all tested as a univariate model, meaning it looks at one variable at a time. The obvious next step is expanding this to complex multivariable models, integrating wind, rain, and solar radiation all at the exact same time. Researchers also plan to feed the AI multi-site data from across all of Indonesia, and ultimately they want to compare it directly against traditional ensemble-based forecasting methods to see if this could genuinely become the new operational standard. We've just seen how a foundation model, when it's properly tuned by an automated mechanic, can take the wild, nonlinear dynamics of a tropical climate and map them with stunning clarity. So I'll leave you with this. If AI can master the absolute chaos of our atmosphere, what complex, unpredictable system will it conquer next? Thanks so much for joining me for this explainer, and I'll catch you in the next one.